Good morning, students. Am I audible? Okay. Last class we discussed about the cantilever beam with point load, right? Point load at the free end, then point load at different position. Hope doubt is clear. If you have any doubts, you can type now also. So now we'll discuss cantilever beam with UTL. Okay. I'm sharing my screen. Let me know if it is visible or not.
In this tutorial, I am going to teach you. Didn't subscribe my channel, please.
Screen is visible. I have shared the screen SFD and BMD of a cantilever beam carrying UDL. Okay, so we'll discuss this problem cantilever beam with UDL spanning over the whole span of length L. Okay, so let's start this problem.
At end A and free at end B, carrying a UDL of W per unit length over its entire span. Now let's
Now,
consider
sound
a
is okay?
section XX at a distance of x from the free end B and consider the right portion
Now,
of this
sound is okay?
section. The shear force at this section will
Shivan?
be equal to the resultant of forces acting on right or
Sound
left
is
portion of
okay?
this assumed section as
Madhushmita?
per definition of shear
Shivan?
force.
Okay.
According to
Yes,
which
ma'am.
B carrying
Okay,
a
okay, okay.
UDL
So
of
let's start.
W per unit length over its entire span. Now let's consider a section XX at a distance of x from the free end B and consider the right portion of this section. The shear force at this section will be equal to the resultant of forces acting on right or left portion of this assumed section as per definition of shear force, according to which the shear force at a section is equal to resultant of forces either to the right or to the left of that section. But the resultant force acting on right portion of this section XX is W into length of this right portion, which is equal to WX acting downward. And since this WX lies in right portion of this section XX, it will be considered positive as per sign conventions of shear force. Hence, the shear force at this section XX is positive. Let Fx be the shear force at this section XX. Fx will be equal to plus Wx, and let's mark this as equation 1, which clearly indicates that equation first follows the straight line rule, which means the shear force diagram for this span will be a straight line. Now at point B, the value of x will be equal to 0. So shear force will be equal to W into 0 equal to 0. and at point B x will be equal to L. So on substituting x equal to L in equation first, we will get shear force equal to plus WL at point A. In order to draw the shear force diagram, we will start from drawing the baseline AB. Since shear force at point B is 0, so we will mark this point as 0, and at point A the shear force is plus WL. So we will draw plus WL to some scale and we will join these 2 points. This will be our resulting diagram. For a clear view, the shear force diagram will look like this. And since we got the positive shear force, so SFD will be drawn above the baseline. Now let Mx be the bending moment at the section XX. The bending moment will be negative as the moment due to this load Wx will be clockwise for right portion of this section XX as per the sign conventions of bending moment. And also the beam will bend in a manner that the convexity will be at the top of the beam. It should be noted that the UDL of a section is converted into a point load acting at the center of gravity of this section. The bending moment at section XX will be given by Mx equal to minus times total load on right portion into distance of center of gravity of right portion from X. So Mx will be equal to minus times W into X into centroid of this loading which is acting on right portion of this section XX, which is equal to X.
So I would like to stop here. So let's start with the shear force. Okay. So in the same way, we have section A to B. So we'll consider one section XX between A and B will be sufficient to determine the shear force and bending moment. Okay. So for the shear force, so it will be, as we have discussed earlier, for the UDL, what will be the force? Usually load is provided W per meter length, right? So to convert this load into this load per meter convert to into kilonewton, what we do? We multiply the load with the distance. Okay, so this load will convert it into kilonewton. So same here, if I want to find out the shear force at this section, suppose I am taking a section of XX at a distance of x meter, this x meter. So what will be the shear force due to this UDL? It will be W into the distance it is I have considered. Okay, the load is W per unit length. So as I have considered a section of XX at a distance x, so on this section, how much will be the shear force? It will be W into x. Suppose I am taking a section here. Suppose I am taking a section here of XX at a distance of x from the free end. Okay, so now here also my shear force will be total load, which is W per unit length. So I will multiply with x as a distance. So this will be my shear force. Okay, so for UDL we know that we multiply with a distance to find out the shear force in kilonewton. As this is a positive shear force, so the diagram will be in upward direction. Okay. Now if you consider a shear force at x equals to 0, that means here the distance will here x is equals to 0, so your shear force will be W into 0, it will be 0. Now when you replace this x with L, that means this distance whole, your shear force will converted into W into L, and as this is a positive value, so you will get a positive shear force diagram. So this will be your, at x it is 0, at A it will be W into L. So your shear force will be this one. Okay, this will be the shear force for cantilever beam with UDL. Clear? Now let's move to the bending moment diagram. Again, one section between A and B. You can take section here, here. Everything will the section here and here will be. It will give the same result. So they have considering it is written that the bending moment will be negative as the moments due to the load Wx will be clockwise for right portion of x as per the sign convention of beam, and also the beam will bend in a manner that the convexity will be at the top of the beam. So your convex will be at the top of the beam, so it will give you a negative bending moment. So the total load on right portion into distance of CG of the right portion, that means your For bending moment, we know our load is W into X, right? We saw in our shear force that our load is W into X. So what we do to find out the moment, we'll multiply this moment with a distance, right? And we know for the UDL portion, what we do, we take half of the distance. If you recall your earlier classes, for the UDL part, what we do, we multiply load into distance, and we used to take that distance, half of the distance. So W into X is your load, and the X by 2 is the distance. So your equation will become Wx square by 2. As it will give a clockwise, so they are considering as negative, so it is a negative moment. So as you see, this is x square, so it is so when you'll get in UDL, when you get x square, then just know that it will follow the parabolic law. That means it will give a curvature of parabolic. Your bending moment diagram will follow a parabolic curve. Okay, when you draw a bending moment diagram, it will follow a curvature. So if you replace this distance x equals to 0, you will get a bending moment at 0. That is at B, your bending moment is 0. When you consider at x equals to L, their bending moment will be W. If you replace this x with L, WL square by 2. So if you draw bending moment diagram with these two values, you will get, as it is a negative bending moment, that's why it is in negative direction. So when you join it, as we have discussed that this will follow a parabolic law. So join like this. Okay. So this is your bending moment diagram for the UDL cantilever beam with UDL. Okay. Any doubts from this part? Hope no one has doubt. So let me share the another problem.
In this video, we'll try to understand how load is as shown over here. Now the arrangement for the beam is as shown over here.
So see, earlier the last question we have discussed, their UDL was spanning over the whole span. Okay. Now in this problem, your UDL is spanning over half of the span of the beam. Okay, so we know how to solve that problem when you will be given a UDL over the entire beam. So now let's see another type of problem when the UDL is given over the half of the span. Okay, don't get confused. They have just rotated the beam in this side. You can take this side also, not an issue. The solution will be same. So let's see how to solve this kind of problem when the UDL is given over the half of the span. Okay.
So there is a uniformly distributed load acting for a half of the span length, that is L by 2 from the free end. So AB carries a UDL of W kilonewton per meter, and we have to draw the shear force and bending moment diagram for this particular arrangement. Now the conventions that we are using for shear force diagram, they are upward forces, they are considered as positive, whereas downward forces, they are considered as negative. Now shear force at A will be 0 because this is the starting point for the UDL. At B it will be W multiplied by L by 2. Now as it is acting in the downward direction, we have considered the minus sign, so it is minus WL by 2 kilonewton. Now shear force at C will be same because there is no other load that.
So if you see, they have considered positive as upward as positive and downward as negative. So if you see the at A, there is no any load, so shear force will be 0. Now shear force at B, that means if you take a section here, let me draw a section here. So if you take a section here between A and B, suppose I am taking a section here, XX at a distance of x meter. What will be my shear force? It will be W into X, right? But if you replace that B, suppose they are showing you, they have not shown the shear force between A and B. They just simply wrote what will be the shear force at B. That means at B. So for B, at B, what is my distance? It is L by 2. So they have replaced that X with L by 2. So don't get confused. And they have considered the downward as negative, so it is minus WL by 2. Clear? Again from B to C there is no any other load, so the shear force will be same. The shear force at B will be the same with C. Okay, it will have the same values because there is no any other load between A, B and C. So have you understood this part, these three terms, how they have find out the shear force at A, B and C? No one responds, so I'm assuming that everyone understood this part, and I expect no one asks me again to teach these classes. Okay, understood? You can type in the chat box. Okay, so let's move. So that is, these are the shear force at different points. So let's
L by 2 kilonewton. Now we have to draw the shear force diagram. So we'll start with point A, it is 0 at point A. At point B it is minus WL by 2, remains same over the another length. So we can say that as it is below the baseline, it is negative diagram, negative shear force diagram. So at A it is 0, at B it is minus WL by 2, and at C it is again minus WL by 2 kilonewton. Now we'll have to draw the bending moment diagram for this particular arrangement. For the bending moment diagram, first we'll convert this particular UDL into point load. So UDL is W kilonewton per meter. That is for 1 meter length. The load that is acting is W kilonewton. Now this particular UDL is acting for L by 2 length. So W into L by 2 will be the total UDL length, and it will be acting at the center of this L by 2, that is L by 4. So we will simplify this particular diagram. So our UDL load is W into L by 2 and acting at the center, that is L by 4. So we can say that this is our uniformly distributed total UDL, which we have converted into point load. So it is W L by 2 and acting at half of this particular length or center of this L by 2, that is L by 4. Now the conventions that we have used for bending moment diagram, they are clockwise positive and anti-clockwise negative. Bending moment at the free end, that is A, will be 0. Bending moment at B, now we have to consider this particular point load. So this point load is WL by 2 and the perpendicular distance is L by 4, and it will produce the anti-clockwise moment about B, so it is negative. So minus W L by 2 into L by 4, so it is minus WL square by 8 kilonewton meter. Now bending moment at C, so again on the left hand side of C there is only this particular point load, so WL by 2, but the distance from this point up to point C will be L by 4 plus L by 2. Now L by 4 plus L by 2 is nothing but 3L by 4, so we can say that it will be nothing but 3 by 8 WL square. kilonewton meter. Now we'll draw the bending moment diagram for this arrangement.
So for the bending moment part, let me discuss with this one. So here for the bending moment portion, they have considered clockwise as positive and anti-clockwise negative. Okay. So what they have done, as we have discussed in earlier problems, that we can replace this UDL with point load. So what they have done, they have replaced this point load UDL with point load of WL by 2. Okay. How? UDL was, let me annotate, UDL was given W per unit length, or the length was given of the UDL was, it was spanning over L by 2. So what will be the point load? W into L by 2. Okay, so they have replaced this UDL of W per unit meter to W into L by 2. So this is the UDL, and they have placed this point load at a half of L by 2. That means L by 4. So hope this part is clear. So next, at A, your bending moment will be 0, and at B, your bending moment will be this load into distance. This load, it is acting at a distance of L by 4 from B. So when you multiply this, you will get WL square by 8. So your bending moment at B will be WL square by 8. Now bending moment at C, how much it will be? Bending moment at C will be, there is only one load, WL by 2. Now this WL by 2 is acting at a distance of C, how much? This is one distance, L by 2, plus this is the distance, L by 4. So this will be the bending moment at C. Understood? Bending moment C, it will be WL by 2, L by 4 plus L by 2. As it is giving your anti-clockwise movement, so that why negative. So when you solve this part, you will get bending moment as minus 3 by 8 WL square. So when you draw, you will get a, since between B and C there is no load is present, so this will be straight diagram, and this part will be, as we have UDL, so it will be a parabolic. Any confusions from this part? Any doubts from this part? Your sessional will be on 7th, second session. Mechanics of materials will be on 7th, 9:30 to 10:30. Okay. So any doubt? Okay, no doubts. Good. So all of you can write your roll numbers if you don't have any doubt in this part. So in the next problem, what I'll do, I'll place a point load here. Okay, you have to solve that. I'll place a point load here, then you have to solve. Don't leave the class, just write your roll numbers. Okay.
to draw point loads as shown over here.
So as we have time, we can discuss this one also. It will take 5 minutes of time. So screen is visible? Is my screen is visible? Let's discuss this problem. Cantilever beam with UDL and a point load. Okay. So shall I start? Okay. So a cantilever beam with UDL and one point load.
So it is carrying a uniformly distributed load UDL of 0.8 kilonewton per meter at a distance of 1.5 meter from the free end. So this is the free end and this is the fixed end, and a point load of 2 kilonewton at a distance of 1.5 meter from the free end. Now, because of this particular downward acting load, the reaction is RA at point A, and the reaction we have to calculate. So first we'll draw the shear force diagram. The calculations are done by assuming the conventions that upward forces are considered as negative and downward forces they are considered as positive. Now, as there is no force that is acting at point B, therefore shear force at point B is 0. Shear force at C right, CR means it is C right. So just at the right of the C, without taking into consideration the effect of this particular point load, will be 0.8 multiplied by this 1.5. So this is 0.8 kilonewton per meter. That is for 1 meter length, the load that is acting or force that is acting is 0.8 kilonewton. So if you multiply it by 1.5, that will be the total UDL load that is acting from B up to point C. That is just at the right of this particular C. And as it is acting in the downward direction, it is positive. So we have considered downward positive. So it is 1.2 kilonewton. Exactly at point C, suddenly there is a point load again acting in the downward direction. So 1.2 plus this particular 2 kilonewton point load. So that will be 3.2 kilonewton. From C to A, there is no other force that is acting. So we can say whatever the shear force that is there at point C, the same will be acting at point A. So shear force at A is also 3.8 kilonewton. Therefore, the reaction that is offered, correct, will also be equal to 3.2 kilonewton. So RA is equal to 3.2 kilonewton. Now we'll draw the shear force diagram by taking into consideration all these particular values. So at point B it is 0, whereas at C right it is 1.2. So there will be an inclined line. Then there is a point load, so there will be a straight line of 2 kilonewton. So total load will be 3.2 kilonewton. There is no other force that is acting between C and A, so there is a horizontal line. And at point A, the shear force is 3.2 kilonewton. So these are the corresponding values which we have already calculated over here. So in this way, we can draw the shear force diagram. Now we'll see bending moment calculation and the corresponding diagram also. So for the calculation of the bending moment, we'll convert this particular UDL into point load. So 0.8 multiplied by 1.5 is the UDL load, and allow it to act at the center of this particular 1.5 meter length. So in this way, we can convert this UDL into point load for the calculation of the bending moment. So bending moment at B is 0 because it is the end point of this particular beam. Bending moment at C will be due to this particular load, that is the UDL load which we have converted into point load. So 0.8 into 1.5, that is the UDL load, and from this up to point C, the perpendicular distance is 0.75. So 0.8 into 1.5 into 0.75, and again it will produce the clockwise moment over here. So as you can see, this will go over here in the clockwise direction. So it is producing the clockwise moment, and we have considered this clockwise moments as negative. So therefore this value is negative. So shear force, or rather bending moment at point C is minus 0.9 kilonewton meter. Similarly, we can find out the bending moment at point A. So again, we will take into consideration the load, that is
बर्फाने
0.8
दिया
into
लेकिन
1.5 kilonewton, that is the UDL converted to point load.
ये तो
From this up to point A, again it will produce a clockwise moment. So from this point up to this point, the total distance will be 0.75 plus 1.5, and the load is this particular load, that is 0.8 into 1.5. So 0.8 into 1.5 and perpendicular distance is 0.75 plus 1.5, and again it is producing the clockwise moment, and that is negative. So this will be represented by this first term over here. Then this point load, it will produce again the clockwise moment. So 2 multiplied by perpendicular distance is 1.5. So that is represented by this particular second term. So the total answer is minus 5.7 kilonewton meter. So in this way we have done this bending moment calculation. Now, as from B to C there is a UDL, it is a second order equation. So here there will be a parabola and there will be an inclined straight line, and the values are 0.9 kilonewton meter and 5.7 kilonewton meter. And as these values they are negative, we have drawn this diagram below this particular reference line or baseline. So in this way we can draw the shear force and bending moment diagram in case of the cantilever beam carrying UDL as well as the point load. Thank you very much for watching. Do subscribe to our channel. Thanks.
So have you understood? Hope this part is clear also. So if you have any doubts, you can type in the chat box. Hope everyone wrote their roll number. Okay, see you in the next class. Next class we'll discuss about deflection of beams. Okay, we'll revise that deflection of beams with different methods of solving on deflection of beams, and I'll share the syllabus after some time for second session. Okay, it will be the same mode of like earlier Google platform. Okay, thank you.